Okay, I'm ready.
All right. Hello, everyone. Welcome to another life science stream today. We have a community guest, Sam Rodkey, who is going to, many of you will know from our community, he's been quite active trying out our hypergraphic writing packlet. And we are going to be getting into some applications and possible bridges between physics simulation and the kind of rewriting that we are used to doing. But first of all, maybe Sam, why not you go ahead and introduce yourself and tell us a bit about who you are, what you do, and where you come from, kind of thing.
Yeah. So first of all, thanks for having me on your live stream. Really appreciate it. And been watching for quite a while. Long time listener, first time caller, first time I've ever been on a live stream, obviously for Wolfram. So I'm kind of it's kind of surreal having you guys talk to me. And after watching you for probably my kids kind of know you as those scientist guys you like to watch YouTube videos about. So they actually asked me at breakfast today, like, "Oh, are you gonna go talk to your scientist friends? That'll be cool, right? Yeah, it's gonna be a cool day." So, yeah, no, I'm really happy to be here. My name's Sam Rodkey. I'm an engineer. I've worked in kind of the aerospace engineering field for the last 15 or so years. Don't have any formal training in hypergraph rewriting systems whatsoever. Have a lot of kind of applied experience with meshing, modeling and simulation for engineering applications. So think like finite element analysis, computational fluid dynamics, different ways of modeling physical systems, either at a macro scale or kind of a micro scale, using computational methods, numerical methods. So I started to see some analogies with hypergraph rewriting systems, and so I'm here to kind of talk to people who are way smarter than myself about these ideas and see what they have to say. So.
Well, Sam, that's fantastic. Thank you so much. I really appreciate that enthusiasm, and I want to say that as I've said in writing in our community, that this is kind of a first in a way that we're having some technical individual in our community that joins one of our live streams. This is really the sort of template of the collaboration that we like to build. The science we do is open, and this is really the spirit of open science. And I mean, I don't think many of us have any formal training in hypergraphic writing, so in that sense, we are all on the same.
We're all on the same page.
Yes, absolutely. But then at the same time, it's also fantastic that we. I mean, as people know from our project, if you've been following, we have had all this interest in formal mathematics and sort of theoretical physics, and it will be super interesting because in many of our conversations internally, we constantly keep referring to, well, but this really resembles when you try to do finite element stuff and the PDEs, and it's always been kind of in the background. And Stephen Wolfram himself was mentioning this constantly. Probably Nick remembers him constantly saying about fluid dynamics. Oh, we should do this for fluid dynamics. Blah, blah. Like it's constantly bringing that example up. So your comment came at a very timely moment because we thought, okay, there's a person with interest in this, and we have had this in the back burner for a while. So let's just go ahead and try and build proper analogies, and let's try to explore this space. So I think a good starting point would be a little notebook that you've prepared, Sam, and maybe you can walk us through your ideas, and we can take it from there.
Go ahead and pull that up here. One moment. Okay, hopefully you guys are seeing a Wolfram notebook. So
not yet.
Oh wait, I gotta confirm. Hit share. Yeah, sorry.
Yeah.
There we go. Glad
That's
I asked.
Right.
Okay, so total caveat, I have written like 0 Wolfram language code before about 2 weeks ago. So maybe I played with it, dabbled with it in grad school, but haven't touched it a lot since then. So I'm probably going to embarrass myself for those of you that are like ninjas of this stuff. So if I'm doing something dumb also, just for my own education, please just let me know. I have this secret goal for this live stream that you guys will show me how to do it the right way. So if you see mistakes that are easily avoidable or interesting ways to jump off from here, please chime in and tell me I'm doing it wrong. Okay, so also this may crash. I've had issues with my MacBook Air, which is kind of underpowered, kind of running stuff. So I think this is one thing I didn't know before asking you guys in the support chat. How do I actually install these packlets? I kind of searched the documentation in the Wolfram site and these specific packlets because I think they're kind of experimental, right? Have this special process to install them. So if you're like where I was a couple weeks ago, this is the magic incantation. I'm not sure I'm not sure if you guys posted this somewhere where people can find it. I know it's in the support chat somewhere. I feel like I asked about it in the support chat. So that should make it easier, hopefully, for folks to install it. Okay, I'm just going to rerun all this. Okay, so I kind of wrote an intro here so I didn't embarrass myself too bad. But the question that has been burning in my brain since you guys kind of planted the seed a couple weeks ago during a discussion is, can you use a purely hypergraph representation and a rewriting system to emulate solutions to partial differential equations? And like, at first, this seems like a really esoteric goal, or like a goal that doesn't have any significance. But I kind of tie it back to during the pandemic watching Jonathan and Stephen's live streams. And Stephen would always say that the limiter for a lot of what they're doing is the absence of this sort of like fractional dimensional calculus. And I think that you guys are kind of pioneering that fractional dimensional calculus. But I have this hunch, it's not even a theory. It's not even like based on anything other than an intuition, maybe, that if we were able to take hypergraphs that kind of look like 1D domains, 2D domains, 3D Cartesian domains, 3D like polar coordinates domains, and are able to come up with rules that can essentially emulate the physics of basic PDEs that we all learn in grad school, that we know the analytical solutions to, that may give us the ability to then extend those rules to fractional dimensional domains, which we kind of know with these hypergraph structures are really just changes in the graph to kind of topology connectivity, right?
Yeah.
Have I embarrassed myself yet? Hopefully not.
No. May I just tag along the comment?
Go right ahead. Yeah.
No, it's just to reinforce what you just said. I think it's excellent. I think it's perfectly framed, and it coincides with the effort that we've been advertising since we began. So Stephen had this idea of what he ended up calling infracalculus, and so this word infra has been thrown around a lot, and so we now attach it to geometry. But really, you can just think of infra as a general approach to like infra algebra or infracalculus, infra geometry, all this kind of stuff. So this is exactly within the scope of what we believe is going on. So I'm glad that you had this hunch or this intuition, because it is exactly aligned with what we were thinking internally, and I was thinking, it seems that these systems are performing some kind of mathematical processes, but they seem to be sort of machine code level, and they're much more fundamental in some sense, and therefore much more noisy when taken as a whole, right? If you see the whole thing, it's like, okay, there's a lot of noise there. There's no clean sort of polynomial solution or exponential solution or something. So yeah, it's just to reinforce your point. It's absolutely aligned with what we thought.
Yeah, and so I think the piece that made me kind of get off the couch and start messing with this and spamming your chat with wild diagrams and stuff was sort of this observation that if we take a moment and just kind of ignore, we know that these hypergraph edges can evolve, and the actual connectivity of these graphs with certain rewriting rules can dramatically change with successive rewrites. If we take that paradigm and say, okay, let's hit pause on that. Let's just imagine a graph, like or a hypergraph, where the simple edge connectivities are kind of static, and that kind of looks like a mesh in a lot of conventional, computer codes for solving physical equations, right? So I can make a mesh that looks like, I have a diagram here somewhere. I can make a mesh that looks, man, I'm killing my surprise here, like skipping all this stuff. But I can make a hypergraph that essentially looks like a 2D domain mesh, right? Like everyone learns how to do this stuff, I think, in undergraduate physics and engineering, usually, like, how do you solve the heat equation on a 2D lattice like this with this regular connectivity? The only thing that makes this 2D is kind of this regularity of the connectivity, right?
Yep.
With the exception of the boundaries, every node is going to have 4 neighbors. That is the rule, right?
Yep.
Hypergraphs can be much more exotic. This one could have 80. This one could have 1. This one could, so it's just almost like hypergraphs are almost like, to me, an extension of lattices and meshes that people have already been using for years to solve these kind of spatial differential equations. Okay.
Yep.
So the piece that I was like trying to figure out was, how do you store the field values if all you have is typically you want to solve the heat equation. So you need to store the temperature at each of your nodal locations to kind of initialize the system and then evolve it forward through time. So, okay, I'm not allowed to go have a vector of temperatures, right, in float 64. So what do? Right? What is the means by which we can encode like a scalar field that is associated with or defined at each of these nodal locations? So like maybe my only thought was like, hey, it'd be pretty cool if you could. You gents were talking about multiplicities as sort of like a fundamental operator on hypergraphs and a way to, you know, store data or recover data from simple rewrite transformations, right?
Yeah.
So my thought was like, okay, what if I just shove 8,000 unary edges at one node? That's almost like storing an integer value of 8,000 just from the multiplicity at that single vertex. Now it's kind of insane, right? At some level, when you start doing that at that scale, right? I've actually not tried to draw that with the Packlet, so maybe we can crash my computer if I try and do that. But I was kind of like, wow, if you could store, you could use this multiplicities, and unary edges to me kind of looked more like data about a vertex or a node than data about a relationship between two nodes. So I kind of felt like I had this hunch like, okay, well, I can encode these scalar fields at each of the nodal locations by just distributing unary edges, sprinkling them throughout this graph in some initial condition. And then, I kind of had maybe an even crazier idea is like, well, what if I wanted to encode multiple different scalar fields at once? I could have, and this maybe isn't a great idea, but you could also do like higher arity self loops, like imagine unary edges are just the subset of like arity. Oh man, I'm going to embarrass myself. Arity 1, right? Mm-hmm. Like yep. It is a self loop with of one. Okay. Yep. But then like I could have a binary edge that just loops back on itself. And that's almost like an independent variable. The multiplicity of that could be treated independently from the multiplicities of unary edges. And then if you take that to its limit, I think you guys were talking about this the other day on a live stream, having these arity, really higher order arity structures. You could have a self loop with six nodes, all of which are the same node. That's almost like some sort of sixth order or a six. You could store six independent fields on top of each other, but just by taking multiplicities by arity. Okay. Yeah. So far, all of this is possible, but is any of this a good idea, and will it amount to anything at all? Still wasn't sure yet, but started spamming the chat. So then I was thinking about something that Carlos kind of in passing said in one of the earlier live streams about sort of a flow rule, a simple flow rule. And it was just this, if I recall correctly. And he even had the diagram of this, which is, hey, if I have a unary edge, I can always rewrite it and it kind of flows. And then I was kind of thinking to myself, if you connect that with the fact that I could store, 800 unary edges here and 600 here, this starts to me to look almost exactly like a diffusion equation or a heat equation. So if you go back to your undergraduate physics education, the amount of flow of heat is proportional to a spatial difference in temperature between 2 points, right? So, or the flux, the instantaneous flux of heat is just Fourier's law of conduction, right? Yeah. So this to me kind of looked like things I was doing with like circuits are kind of similar. Like what if these unary edges encoded a voltage, a potential, right? And then as they move, that's a current. Mm-hmm. Like you could emulate a number of very simple either spatial systems of PDEs or even systems of ODEs that are derived from like graph-like structure. Like if you've ever taken engineers always take this, a linear circuits class, right? Where you learn about how to derive rate equations for a connectivity graph of nodes and different elements along each edge, like a resistor, a capacitor, et cetera. But these are like structures that have no spatial there's no spatial locations in a circuit diagram. It's purely connectivity and it's purely graph kind of theory. So I was like, man, this looks like a lot of stuff I have. This rule itself looks a lot like stuff I've seen before, and I may not be that smart, but I know these simple systems enough to like catch that there's something interesting about this. So so yeah, I started to explore this rule in particular. Okay, so I don't know. I feel like I'm talking too much. Any
No,
like
I'll just make one comment. I mean, the flow is excellent, so I will just keep you going. But when you mentioned the possibility of encoding higher arity self loops to for example distinguish different unary-like entities.
Yeah, field quantities or something, right?
Yeah. So that's one technical possibility. We are kind of trying to shy away. At least I am. I want to speak for others. At least I am trying to shy away from self loops in practice. But another way that we are assuming that things can have tags or labels that allow you to effectively, when you declare a hypergraph, you need to essentially designate the elements in your hypergraph. So you can't just say I have like different colored unary edges, and each color represents a field. So effectively, they carry different labels, and they are basically unique IDs that allow you to distinguish between two kinds of edges.
So I have maybe a hot take on that one. You guys tell me if this is too hot a take. I think you're doing this because of the spinal graph representation. Is that true? Because in the spinal graph decomposition of this scenario where I have like a unary edge and a binary self loop, when you go to spinal graph mode, you can't tell the difference between those two things.
Exactly.
You can't distinguish them.
That's that's one of the big reasons. Yeah.
Okay. I kind of wanted to make you say that out loud because I suspected that was the case of like, you seem to be corralling me away from this idea, and I'm trying to figure out why. But now I think that's fair. But
there's no. I just want to say that there's nothing wrong with self loops in principle. Sure. Like they can be part of the expressiveness of hypergraphs. I think that's perfectly fine. But it's more than like now we are in a phase where we are really kind of rethinking our objects in the Packlet itself, like how we are going to implement them and wire them. So, but there's nothing wrong with like self loops in terms of like
I'm your edge case just coming in breaking all your stuff. No, I want Arity 8 self loops. No, I want it tomorrow. And then
that's great.
So happy I could be the I think there's like some at Netflix or something, there's some software library called Chaos Engine or Chaos Monkey, and it just like goes and clicks everything you're not supposed to click in the wrong order, and it just breaks everything. So I'm glad I could be that for this project. That would be my claim to fame. So yeah, this flow rule. Okay, what is up with this flow rule? I think there's kind of some interesting properties of this, and I think you mentioned a number of these. So I'm not saying anything new here. So, it conserves the unary edges. Okay, that alone is kind of interesting. There are a lot of rewrite rules where edges are not conserved, and there are a lot where they're transformed into some other thing. And so this one is interesting because it kind of has a preservative property of like the number of simple edges is constant through rewrites. And the number of unary edges is constant throughout the domain across rewrites. So that actually makes the computer science part of this way easier, because when I was doing these like large scale simulations, there was zero allocations. I have a fixed length vector of like a list of self loops and a list of simple edges, and I'm just like flip-flopping things around, and there's no memory allocation. So I thought that was like kind of cool. So it never actually terminates. So I thought this is actually the most interesting thing from looking at this for a long time, which is there's been a lot of discussion and maybe assumptions about these rules have to be confluent and have to kind of terminate, right? Like, or they have to all reach some state, or there's like this huge space of states you can be in, but they kind of converge into a confluent state. But in the case of this rule, there is no terminating state. It's almost like now there is a concept of an attractor and kind of an equilibrium state, or a state that there's a lot more transitions to it than from it. Or there's like and maybe we could explore this graphically in this live stream. If we could actually make that graph, that'd be great. But like what you'll see is that for this rule, the equilibrium state is these unary edges all being uniformly distributed, but you won't stop. Like then you'll flip-flop, put the potential back, and oscillate, kind of about that condition. And sometimes you'll build up a deviation from the equilibrium state, but you'll kind of have a tendency to return to that ground state. So it kind of looks like a lot of there are analogies here to like kind of chemistry with like reversible reactions where there's forward rates and backward rates. And I started to look at this with path counting. I did a really terrible job, but we can maybe do a better job on this live stream. But there is this concept of equilibrium. There's like attractors for this rule where you kind of approach an equilibrium condition, but you'll never stop there. And then the other thing that I think was kind of subtle is if you think about it, this rule matches in proportion to the imbalance in unary edges across a simple edge, right? So remember we were talking about Fourier's law of conduction, where the instantaneous flow rate through space, right, across a spatial difference is proportional to the instantaneous temperature difference across that same delta in space. And I was kind of thinking about this, and if I have 3 unary edges here, actually this is a great time to hop into some live coding. So I may put you guys on the spot and ask you to help me do something here.
Yep.
So let's start with this flow rule, right? Let's start with this initial condition. I've got 3 unary edges. It may be hard to see here. You guys tell me if this is visible. I can make it bigger, I think, if we need to.
Maybe a bit bigger, but yeah, we can see it.
I'll make it a little bit. I'll go to 200%. Here we go. So there's like 3 circles. This is beyond 3. It's kind of hard to tell what's going on, I think, with these unary edges. That's not your fault. That's because I'm the psychopath trying to put 800 unary edges in a single vertex. So let's start with a simple system. So it looks like a 1D domain, right? I have 2 simple edges here, and I'm starting with these 3 unary edges all bunched up on one side. So like, think about it like this. I have a bar of metal, and on one side I apply a massive impulse in thermal energy. I don't know how this is happening. Magic. We'll just say magic for now. Simpler than trying to define it. So for the folks who are like me who have no idea how this works, and who have no background in Wolfram language, the hypergraph packlet is great because you just encode a hypergraph. You pass the first argument is just a list of edges, which kind of look like, to me, they just look like tuples from another language, right? Like a list of tuples here. And that defines a hypergraph. And then you get this awesome visualization of it. And it's like 0 cognitive load. It's great. So kudos to you gents for making this look great. And then what I want to do is I want to define the multi-way system of that initial condition. And I want to apply the diffusion rule, which is up here, sorry, I kind of skipped over this, where if you want to declare a hypergraph rule, it's essentially the tuple, the list of edges for before and the list of edges for after. And then this third argument is kind of some secret sauce that maybe we should talk about at some point soon, because I think there's something in there that I don't fully understand, but it seems to do some things that I want it to do half the time. But with this rule, you can kind of store it. I just store things as variables because I'm probably weird. But then I'm going to create a multi-way system that's the combination of that rule matched with this, applied to this initial condition. And then beyond that, I can do things like, I don't know, what I would love to show is what's the one where you can show all the matches? It's like the evolution graph.
Depends what you mean by a single step, right?
Like I'm going to do a single step, but I think what we want to show is all of the possible like rewrites from this initial condition. I think it's just evolution graph, and then it shows you the before, and then each of the
states graph.
Maybe. Diffusion rule isn't defined.
Yeah. You need to run
I didn't rerun everything.
Yeah.
This is the one danger of notebooks is I should probably just run the whole notebook if that doesn't crash my machine. Okay, cool. Now this is like enormous. Okay, we may have to do some resizing here. Hang on one second. Okay, so we start with this initial condition, and then if you scroll down for 3 years, here's the second condition, right? I thought this looks like a states graph though. Did I do this wrong? I thought I did evolution graph. What? I thought there was a I feel like I'm doing this wrong already.
Well, it will depend on how it canonicalizes. If it's like the hypergraph looks exactly the same, it would just converge to a single vertex.
Yeah.
So I also have a process here. Whenever I'm confused, my first thought. So this is for all you fellow Wolfram new people who don't know how to do a lot of things. I found this is supremely useful. Hold your cursor over the thing. This little info button pops up, and a window just popped up down here. So it's not as dramatic as if I had this set up all correctly. But then you get the full docs for this essentially application. And my immediate thing is also always to look for the graph name I'm looking for, which I think is, man, I feel like states graph is just states. This is the one I want. Causal graph, maybe? No, not causal graph.
Maybe evolution causal graph.
I think it's evolution causal graph, where it shows the actual, yeah, this is what I wanted. Perfect. Okay, you guys are already showing me the way here. Okay, this doesn't look great because I'm kind of too zoomed in, maybe, or I didn't choose the right vertex size. Maybe I should go like bigger because this is kind of hard to see. Maybe that's too big. Okay, anyway, hopefully it's evident what's happening here.
There's a way to control the size of either those blue vertices or the yellow ones.
Yeah. Oh, this looks better if I kind of just stretch a little bit here, and we'll kind of walk. Okay, so you remember what I said about this rule kind of matches in proportion to the potential. So remember, we have a 3 over here, none over here. Well, it turns out there are 3 distinct ways for us to essentially redo the same rewrite process, right? Because there's 3 distinct unary edges that I could flow to node 2 here, to vertex 2. So that's already kind of interesting because that I'm already starting to see a connection here where if I have a fixed number of rewrites per second, if the universe is really running with some fixed computational rate, then the rate that I see these little unary edges zipping over to their neighbor and that sort of diffusion process happening, the more matches I have, the higher the probability, or if I'm doing a sampling, the higher the probability or the frequency that I'm going to match this rule. So it could be inferred that like that rate is really an illusion of there are more potential matches for a rewrite rule. Okay.
And let me add something here. I think that's a beautiful observation, and I think it matches fully with your proposed hypothesis, which is if you have, say, N and M, like 800 and 300 or whatever, it fully matches arithmetically, right? Because if you have more matches on the other side, and then you don't consider that you only see the end states as distinct if they are distinct, then it fully accounts for the pattern that you're hypothesizing.
Yeah, it's almost like the diffusion equation isn't the governing relationship. That's just sort of an emergent macroscopic like approximation of this even lower level thing that's just doing something even simpler, like almost ridiculously simple when you really think about it long enough. So I thought this was so cool. I stayed up one night thinking about this, and my wife thought I had lost my mind, like honestly. So yeah,
don't worry.
Okay. So I'm not the only one. That's good. That's good to know. Okay. So, but this is with one rewrite. Here we've already drawn three separate paths to the same state. So in this case, it's at least confluent, right? Or it's like the 3 rewrites would all result in the same condition. But here's where it gets interesting. If I rerun this, okay, so for the folks that are still learning, this integer argument here is the number of steps you want to run for. And I haven't noticed, I've never tried to run this beyond like 4 or 5, mainly because the graph gets so hairy that you can't really see anything anyway. But let's try running this for...
Maybe you can zoom out a little. Like we don't need...
Okay, yeah. I almost think it's because I'm super zoomed in on this, I think, a little bit here. But yeah, let's try running it for 2 rules, or 2 steps. Ooh, yeah, it's already getting... I may have to shrink some of this and squint a little bit. Okay, so I need to make this taller. That's the problem. How do you change the aspect ratio of the diagram? Can you do that? I thought you could.
I think if you hold shift maybe, and then start dragging.
That was, see, I'm already learning stuff. This is exactly why I needed this live stream, is to get myself out of these pickles here. Okay.
We're all learning. I didn't know this. So
yeah. So this is what, okay. So this is the only thing that I think is a truism, is like pair programming, honestly, is with a more senior person or a person who has more experience than you, is way underrated in terms of educational value. Like cool stuff per hour is way higher with pair programming than people give it credit. So I'm secretly using you guys to accelerate my education. Okay, so here you see we have those 3 original rewrites to the same state, but after that it kind of explodes in terms of the options that are present, right? We could pull another node over to the middle. We could revert the change that we just did. And this is actually something that I need to figure out how to... 1 minute, I'm going to come back to this question, but I want to figure out how to make the labels do what I think they should do. And maybe it's probably user error. So I have the right people on the call to help me figure this out. But this could revert to the original state up here. And then the third state is I could just take the unary edge that I moved to the middle and move it to the third edge. Okay, so far, yeah, okay, Sam, you could have written all this out yourself. But here's what's interesting. If you run this rule for many steps and you draw the states graph, right? Let's do this and see how well this works. So the states graph is like, show me the network of all the states and all the state transitions between them. I think of this of like a Markov diagram, or like what's the word? Like a state machine diagram where you show all the states that you can transition between. That's obviously what it is. So I hope I'm picking up on things. This is where I usually get confused and this is where Nick actually showed me a cool trick. So far, 5-step deep, this is too much, right? Like this is too much for a human being to process. And the other thing you'll pick up on is a lot of these are redundant. Like some of these are actually the exact same state. So for instance, I'm trying to pick one off that's identical here. I think this one is identical to...
Well, the first 2 at the top, right? The top.
Yeah. Oh, yeah. These 2 are definitely identical. So what I think is happening here, obviously, is that each new rule that gets applied, it's just creating a new state, and it's not treating them as equivalents. So the way you get the equivalents to work out, this is a trick that Nick showed, and it was in the support chat somewhere. Canonical state function, right? And then
in quotes.
You have to put it in quotes.
Yeah.
Well, maybe that's what I've been doing wrong the whole time. It does work without quotes for some reason. We could do it live and see, but I was able to get results with just this. Is that just me being lucky rather than skilled? I don't know.
Well, maybe.
Yeah, I don't know. It's Chaos Engine at work again here. So apparently you don't have to put stuff in quotes and you get results. Okay, so 2 things kind of fall out of this is, oh wow, there's like a really small number of states that we're oscillating between. There's also another thing you'll pick up kind of staring at this graph is there's different numbers of edges in and out of these states. Okay, that to me was very interesting when I first saw this, which is, you remember how I was talking about this concept of equilibrium or this concept of an attractor. Well, it turns out that this attractor property seems to be related to the imbalance of edges in and out. So if a state is in the direction that you're being attracted to on net, there's going to be more edges into that state than out. And maybe this was like obvious to everyone else, but I was like, wow, this is like super cool. It reminds me of like Markov chains, like with state transition probabilities. It reminds me of chemical reaction networks, where you have forward and reverse rates that can be balanced. And then the equilibrium concentration after you kind of run all these rates to equilibrium is kind of proportional to their varying kind of Arrhenius exponents. I can't remember the term I'm trying to think of here, but there's basically a free energy associated with each state transition. And that's like the more forward that reaction is, the higher the equilibrium concentration. You'll tend to move in that direction. Okay. So I was like, wow, this is super cool. I can count these edges. And I think the way I figured this out was just literally like Chaos Engine at work, going down here and being like, what does this do? Edges. Okay. Number of edges. Okay. Well, that sounds like what I want. I'm going to hit that. And then I think there was another way where there was a way to get the edges by the like in and out. I think there was like an in degree.
Vertex in degree.
Yeah, vertex in degree. Now, how did I do this before? I literally lost this notebook because my computer crashed once. So, but at some point, I was able to compute sort of the ratio of the in degree to out degree for each vertex. And I don't know if you guys want to try and do that live here a little bit, but can I take the output of this states graph and essentially compute that?
Yeah.
So it's %32. So try vertex in degree of %32.
Okay, of %32. Here we go. I'm gonna embarrass myself live. Okay, so here's my in degree. Cool. Now, are these are the indices of this corresponding to each other? So if I know there was an out degree also, right?
Yeah, they should correspond. Well, you can't make this.
Oh, you can't do that? You can't do like a tuple? Oh, man.
No, you have to make a bracket.
Okay. So I'm learning things. So the bracket is basically like, hey, this is a pair. Oh, wait, that is not what I wanted to do. I'm not sure.
Just with a comma.
Add a comma. Just add a comma.
Oh. Yeah.
I
told you I was going to embarrass myself on this live stream, guys. Okay. So this was kind of interesting. There are definitely, and I think, did I try and do that? How do you do like a list comprehension in Wolfram language? Like I want to take the out degree divided by the in degree or vice versa. How do I do that at an element wise level? This is probably the dumbest question I've ever had. Just is that going to do it?
Yeah. You don't need list.
Boom. Okay. I told you I would embarrass myself. But yeah, I eventually did figure this out and I just forgot it. But you can see here there's kind of like a spectrum of these in degree to out degree values here, where obviously 3 is much bigger than 2/5. So I don't know which one. Can we put these on these states somehow? Is that a ridiculous thing? Like, could I label the nodes with their in degree to out degree ratio?
Kinda. You can use the vertex label.
Yeah.
Okay. So how would I?
You can type graph again. Graph of %32. Right.
Oh, okay. Let me just. Oh no! What is it like? Insert a new cell. It's like Shift D or something.
Just click.
No, you don't have to insert it. You just start typing.
Just click. Click on an empty, like on an empty line.
In between,
like
in between cells.
Like this thing, right?
Yeah.
Okay, cool. Sorry, I'm so bad at this. Graph %32. Okay.
So that's just going to be the same, but now you can change the options, and one of the options would be vertex labels.
Yeah.
And then I would like map that to this computation, like that.
Like
copy paste.
We'll try to just remove the outer braces.
Okay.
We just put the list. I'm not sure whether that would work, but we can try it.
Well, here we go. Chaos. Oh, dude. I think it. Oh, wait. There's nothing on here.
It's just the first label, I think.
Okay, so I probably have to do the.
Oh, you need to do something more fancy. You have to specify each vertex. So you have to ask for a vertex.
You have to like loop over it.
You can write. Let me put it in chat.
Okay.
It's a short code, but it is kind of.
It's involved.
Not very. It's short, but you need to know it.
Is it like a comprehension? Does the word comprehension mean anything to you guys, like in Python or in Julia?
I know what kind of comprehension.
Okay.
But you don't need it usually. Usually you don't need comprehensions in Wolfram language.
Okay.
So you can make this. If you do the spread.
Which chat is this in? Sorry.
Zoom
is
chat.
This in our chat?
In the Zoom chat.
Yeah.
Okay. Well, you guys put some stuff in the chat that I don't want to put on the screen, so I got to do this carefully. Let's see. Okay. Thread, vertex, list, ... Okay. Let me take a look at this.
Yeah.
Okay.
Just put your ratio of vertex degrees instead of ...
So this, okay, like in the ... you're saying?
Yeah. Without the
braces.
Without the braces.
Okay. Got it.
So that's to make just a list of rules.
So just so I can build a mental model of this, the thread function here is essentially performing this operator on each element of this list? Is that what it's doing?
It's like if you're like a Python person, it's like zip.
Yeah. Okay, so you're saying, but it's isn't it an iterator though? Like where you're doing something on.
Oh, if you have just two lists, if you just have two lists and some infix operator between the two lists,
okay, I see. It is like zip then. So this is okay. So the left here is one part of the pair, and the right is another part of the pair, and then you're just like, okay, gotcha.
Yeah.
Okay, sorry. For folks who do a lot of Python and other languages. Okay, so let's take a look at this. I'm not sure where this one went. It kind of disappeared. Maybe it's just me not doing the plot. Oh, there it is. It's kind of hiding. Okay, so this is kind of what I expected, right? And I never actually made this graph, so I'm like kind of encouraged that I didn't just do all this work to not show something that I didn't expect, that it kind of worked out. But I did do this by hand at one point because I was having issues. So I kind of know it should work out, but like software demos are always dangerous because you never know what's going to happen live. So yeah, so the in degree to out degree is the highest for the equilibrium state.
Nice.
So like that's kind of interesting, right? Like this rule there, you have this attractive kind of property of this state. You'll never terminate there. It's not confluent there, but it has a bias towards it, right? It has an attraction to it. So all of a sudden I'm like, oh, wow, this reminds me of like differential equations and like dynamical systems and sort of like there's all of these relationships to these other things where we have this rule that has this sort of like equilibrium property to it. But it's kind of chaotic. You'll oscillate about it. You'll kind of transition in and out of it. And it's really hard to, it's not simple to, it's not obvious from just looking at this rule that all this behavior is present if you apply it at some scale. So I thought this was like super interesting. And by the way, thank you for letting me be on your live stream to learn how to do some of these tricks. So like I learned about thread. I learned about how to add this stuff to an existing graph. So this has already been, I got my money's worth out of this, if nothing else. So appreciate it.
No, and thank you, Sam, for that, because that's a very interesting and clear illustration of this aspect of rewriting. This is something that we actually mentioned live several times. We're thinking about this sort of discrete diffusion model, and this is just it's a very neat and very pedagogical way to show that state is kind of an equilibrium state. I mean, I'm kind of excited to have such a tangible statement there.
Yeah, I think the one question that I meant to come back to, and I want to confirm this just by staring at the graph, is that I think the labeling of the nodes is not quite stable, if that makes any sense. Like I think of the canonicalization is flipping the graph around and treating things that are equivalent, that if you actually wrote this all out, keeping the 1, 2, 3 consistent, you would not get quite the same result. Like I think the result you would get is you would have more states, because this is kind of squishing a lot of them as isomorphic to each other. I think that's what's happening here. So the kind of question that maybe I have for the people assembled here is, this is kind of a isomorphism property. Like treat things that are isomorphic to each other. I'm using this word, dude, I don't have any math background in this, so if I'm misusing it, like let me know. But
good use so far.
Okay, so like these have the same connectivity graph, right? And even if you blasted away all the node labels, vertex labels, it would look the same, right? With maybe swapping which node is which. So it's isomorphic from a graphic sense, from a graph sense. I would love to have a canonical state function that was treat node labels as immutable, or like, you were having a discussion the other day during the Nodeverse chat, I think, where you were talking about the nodes are the background, they're persistent, they're distinct, and I feel like the isomorphic thing kind of treats the nodes not in that sense. It treats them as things which could be equivalent to each other if the connectivity graph is the same, which I think is sometimes a different aim. I think there are cases where you would want to do either. So
think of it this way.
You're right.
If you need to canonicalize your hypergraph or graph, you need to come up with some universal labeling. In this case, the natural choice is just natural integers. So you have to assign some 1 to 3 integers in a proper way so that even those graphs that have like arbitrary labels, like maybe A, B, C, or X, Y, Z, will map to the same exact labels.
Yes.
If they're actually canonical, so that you can, instead of looking at the connectivity visually, you can just compare the actual edges with those labels, and they would be exactly the same. That's the property that canonization provides you.
And I think that is the part I think that maybe I think that there are cases where you would want to have. I understand that like the concept of canonicalization is like finding equivalences and having a function to true false. Are these two things equivalent to each other? I think maybe the only desire I have that I don't know how to meet yet, and maybe you guys live on the stream will just be like, well, just do X. It's a thing. It's already a thing. You just don't know about it. I'm hoping that's the case. I don't know. And I'll show you a very hyper specific example. So these two things are, if I put these through the canonical state function, right, that exists today, these two states will be treated as equivalent, which is like, okay, cool. That's what I want. I want when one has 3 unary edges and one has 3 unary edges. Those should be equivalent. However, this will also treat the outcome of, and I've got to like search here for like 333. Is there any with 333? I may have not run enough steps.
Yeah, but you can see, for example,
the one where you have all of them on the okay.
Yeah, there are several of them. Like, for example, the one. Where is it?
Maybe one more step is required, I think.
Yeah, I think one more step is required. I'll choose a different example.
I saw a pair. Like, for example, the one at the
this one will be treated equivalent to this one.
That's the example I had in mind. Yes, exactly.
Yeah.
So I actually don't want that.
I agree.
And maybe that's a ridiculous ask, but I wonder if there's a way for us to define a canonicalization function that would be, like immutable nodes or something, or persistent node IDs, or like.
I mean, it's funny you asked for this, Sam, because yesterday Nick and I were having a private conversation, just like a few hours ago, in some sense, like just last night. And this was exactly the point of conversation. It's like there are times where isomorphism, like mathematical isomorphism of graphs, is not useful, and we want this idea of an ID that respects and your structure is actually kept, and then you rewrite on top of it, right? And that's
And so when I was initially doing some of these explorations, I was actually doing this in another computing language, and I didn't even have access to the concept of like a canonicalization function. All I had were tuples with integer values, right? And so the way I would move a unary edge is by replacing, a one element tuple with a different integer value. And so essentially what I was tracking was IDs, but the IDs had a meaning of like 1 always means node 1 and 2 always means node 2. I don't get to blast those away. So for me, that was like a trivial thing to add. And I understand that not every use case you want that outcome. Sometimes you do want to lump all these things into the isomorphic cases. But
so
we're already seeing some
very reasonable.
Sorry.
Just saying.
Yeah.
Reasonable ask.
Yeah. So whenever you come up with that, I would love to be your beta tester. So to remake this plot, because I think there are some more states that are not isomorphic to each other, but are but the canonical state or they're isomorphic to each other, but I want to treat them as separate. And I think there are more states that are hidden when we do the canonicalization. But I think that the trends will be the same. This uniform distribution should be the one with the maximum in degree to out degree ratio is my hypothesis, and sort of one that I've kind of hand calced, and so it should be. So yeah. Okay. So I don't know. Anyone want to grab the steering wheel for a little while or talk or anything? Or I feel like I'm still like rambling like a psychopath on your live stream, and
not at all.
This is great. That's how we feel sometimes.
Well, whether you realize it or not, there are people out there listening. So now I'm terrified to comprehend that like someone out there is like, well, who is this guy? Who is this clown they invited on here? Okay. So the place where my mind goes is hey, the simple relationship and these state transitions are interesting, but what happens if you scale it up, right? Like, what happens if you take the mesh? The first thing you do when you're making like a CFD code or an FEA code is you do these really coarse meshes, right? But then you want the real answer, right? So you refine the mesh, you make the discretization even smaller, and you scale up the computational cost of the simulation, and you explore that, right? Like, or you use that as the real answer. So one thing I did was I took this same sort of linear mesh, this 1D mesh that we had, but I did more nodes. So I did like 25 across, and I played with 25, 50, 100, 10, 5. And I shoved different amounts of, and it's the same construct here where on one side of the domain, I shove all the unary edges and then I just let it run. But what I'm going to do instead of, and this is a point that Carlos made in the chat when we were talking in Discord at one point, was I don't really have the ability to simulate all of the outcomes in parallel. And so what I'm going to use is just statistics, right? I'm just going to sample randomly apply rewrite rules. Oh, thank you, software update. I'm just going to randomly apply rewrite rules and just do that and see what happens, right? So that was kind of my thought process, was start with a 25 deep linear mesh and start all the edges on one side and then run it for millions of rewrites, which I think would not be super feasible within the Wolfram hypergraph rewriting multi-way system stuff. But if I'm just doing simple tuples and kind of moving stuff around, it's very tractable and just simple computer language. And I ended up making a plot very similar to this very early, which at first you're like, okay, so this is the unary edge multiplicities at each node. Each one of these lines represents one of those nodes in the linear mesh. The one on the very far left side is this blue line. The next one obviously is this orange line, green line. Okay, so the first thing staring at this graph, you're like, cool, Sam. What is this? Why is this? Nobody cares. I'll tell you why I care is because it immediately kind of jumped out at me. This looks exactly like analytical solutions to 1D heat conduction problems that I've had to do in the past in a prior life, like almost to a T. And it matches very closely with that sort of 1D diffusion analytical solution. I even think I pasted a link in the Discord where you could go like interactively explore. Like, why not do it live? What could go wrong, right? I'll just pull it up. Like Wikipedia 1D heat equation.
So what are each of those different colored lines? Are those multiple runs or multiple?
So the different lines are the values at each node. So the x-axis is how far in the rewrite process we're at. Okay, so this would be equivalent to your time axis here. Okay, so zoom out for 1 second here, and like all of the unary edges initially are at this first node. So this is starting at some very high value, and then over time it's asymptoting to that equilibrium condition, right? And then it's just oscillating about it. Okay, in a very narrow band. It's not reversing and going to the initial state again. It's just oscillating about this sort of unary even distribution.
But I guess
of unary.
One point is that this is the vertical axis is the value at the original single node, right?
Each line represents a time history of the unary edge multiplicity. Does that make any sense?
Yeah, but since it's a single value, right? It has to be at a single node, isn't it?
Each line is the
node.
Is a vertex, right?
Yes, is associated with a node. Correct. So for a 25 node hypergraph, I have 25 lines here.
Okay.
Does that make any sense?
I see. Yes, I see. Yeah.
The graph is busy. I 100% admit this.
But I did understand that. Okay, now each color goes to each node. That's right.
Correct. Yeah, and I didn't put a legend on here because it would just be like ludicrous. It would take a minute of the graph.
Yeah. So just a quick question. I need to jump after this, but I just wanted to find out the randomization of the rewrites. How did you randomize? Is it just a built-in random function?
So I'm just using Julia code. So Julia has a Murzin twister default random number generator, and I just use a shuffle.
Is it pseudo random?
I'm not sure I understand the distinction there. I go into random and I use the shuffle method and I take my edge list and I just shuffle it. Like sometimes I remember to put a explicit seed in there and sometimes I don't, but I think the default one is literally called the Murzin twister, and beyond that I have no idea what it is. So
very interesting. Okay, this is fascinating stuff, Sam, and again, thanks for spending the time on this, and we'll catch up again soon.
Yeah, for sure.
Yeah. Bye, James.
Enjoy, guys.
So, but yeah, the thing that should stick out here is there's like after a certain number of rewrites, this thing is within some very close band of like that equilibrium distribution. The other thing is the shape of these time histories look a lot like 1D heat equation solutions when you sample, the temperature at a given point, responding to an impulse in temperature at one edge of the 1D boundary. So this ends up looking very much like 1D diffusion analytical solutions. And if you add enough, it's funny, this graph, if I rerun this 5 times, I'll get a slightly different random walk. But those random walks, when you average them over many, realizations, many, draws, they kind of average out to the analytical solutions, like for that discretization of where the nodes are or what the initial potential is. So I thought that was like super interesting. I kind of made this as like a different way of looking at the same thing, where the x-axis still is time, the y-axis is your node index. So you could see like all the unary edges, and then the color is like the heat, right? It's the unary edges, right?
Yeah.
And that heat is just diffusing out until it's effectively uniform. You see some scattering of like, it's getting hot here, it's getting cold, it's oscillating about that equilibrium, but it essentially reaches some equilibrium value and just kind of stays very close to that. So yeah, I thought this is super cool. I did the same thing in 2D at a smaller scale. So I had like a mesh like this. And this is maybe a place I should probably figure out how to clean this up a little bit. But you could start with these simple 2D meshes, and we could actually make these evolution graphs kind of similarly. But you end up getting solutions for these when you apply the same, when I apply this rewriting process at scale, you get sort of the same outcomes, where you kind of diffuse randomly to an equilibrium state, and then you just kind of sit about there and you don't go back to this initial maldistribution of unary edges. So the ignorant math person I am is like, wow, this rule is really cool. I think there are some extensions here of just applying this rule to different domains in terms of the initial connectivity of these edges that look like 1D spaces, 2D spaces, 3D Cartesian, 3D polar coordinates. And what I'm kind of working through, and I'm just behind on my internal timeline, is kind of doing a detailed comparison of these kind of randomly sampling this rule, randomly rewriting this rule, comparing that to analytical solutions in the same basis variables. So like my plan is to do 3D polar, 3D Cartesian, which I've done a little bit, but I don't have like the result that I can like share today, unfortunately. But but yeah, kind of comparing this to say like, hey, does this actually work as a entirely hypergraph rewriting diffusion code, like at some scale, which I think would be super cool.
Yeah.
So
definitely. And
then I'm really curious to see if we make one of these very irregular hypergraphs, like some 2.7 dimensional thing, how does the heat equation work in that domain? Like, is there even an analytical solution for that? I have no idea.
But
that's maybe a question for Carlos.
One pin on that thought, because I mean this is super exciting, and one idea in that direction is that actually like flip the entire thing, right? Instead of saying I have a hypergraph that I kind of understand because it's a mesh or it represents space that I'm trying to model or something, and I want to have this phenomenon running on it. Instead, I can tell you, well, I have this unknown hypergraph. I know that the rule in a known structure represents whatever, diffusion or whatever it is.
Yeah.
And now you have a very unfamiliar space because it's a very complicated hypergraph. And so you actually probe it with this sort of randomized or statistical. It's almost like some form of in mathematics we'll call it like the rank homology kind of stuff where you run differential equations on spaces to probe them, and the solutions to those differential equations tell you about the space, right? Like in typical fashion, you can tell whether your origin is missing or not in your manifold, if if you have divergent functions at that point, things like that, right? So in an analogous way, you could solve the heat equation for a very complicated looking hypergraph, and the solution being these statistics that you're showing here, and those would be sort of like hypergraph data that can be useful to somehow parse what the hypergraph is doing internally, right? It's very complicated. So just as a point that to pin it to the class of hypergraph analysis tools that people are very much in the business of developing. And in fact, I'm going to be in Canada next week for the Network Science Conference, and this is going to be the whole thing, like hundreds of talks about how to get metrics from hypergraphs. And I think this is a very creative one. And so thanks for the inspiration.
Yeah, and the one that honestly, the thing that made me even attempt like this sort of what happens when you scale it up, because I think there's a tendency with some of these things to stop at these small kind of toy problem scales, when I think the interesting phenomena lie just beyond that scale is really like my sort of experience with lattice-Boltzmann codes. So again, I'm an engineer. There are certain types of problems that lattice-Boltzmann code. So if you're not familiar with lattice-Boltzmann codes, I use that term anecdotally, but I think it's like called cellular gas automata by Stephen, and there's a historical precedent here that he kind of set where you can, if you've ever taken a class on fluid mechanics, the governing equations, the governing PDE are these Navier-Stokes equations. They kind of presume that fluid is a continuum, and that there are these sort of differential relationships between elements of fluid in that continuum and how they're stressed and strained and how they can flow. And from that emerges all of fluid mechanics, whether it's turbulence or everything else. But we kind of also know at the same time, like, fluid isn't a continuum. Like if you put it under a microscope of enough power, like you've got individual little molecules bouncing off of each other, and it's not a continuum, right? So the lattice-Boltzmann codes were kind of a development where you can simulate very low Reynolds number flows using very simple rules. Let's see if I can pull this out here. You just have these simple meshes, right? These like lattice meshes. They call them lattice-Boltzmann codes because the meshes are like any other kind of Cartesian mesh, but you essentially have all these nodal points and you evaluate these simple updating rules. And if you choose the updating rules correctly, you can kind of mimic the collision and advection of fluid flow in a way that is, if you look at it at any individual element, it's not that interesting. But when you zoom out and you do millions of these elements, all of a sudden you get these dramatic, flow separation behavior that's very hard to resolve with Navier-Stokes, with conventional CFD codes. You could do some very exotic problems. And so sort of my thought was like, there aren't really lattice-Boltzmann codes for heat flow, or they're less common, I would say, or less useful. But that wasn't my primary motivation. My primary motivation was like, what does a lattice-Boltzmann code running in a hypergraph substrate look like? And that to me was kind of cool. So I'm not sure what is the right scale of problems to try and simulate within these packlets. Like, if I told you I want to do 1 million rewrites, I'm pretty sure you'd be like, don't do that, please. You're going to crash your MacBook Air. It doesn't have that much, power. But there's probably like some scale that is interesting that you may want to plan for that scale down the road, because I will be the guy being like, why can't it run my 2D million element mesh? Like trying to use it like an engineering tool rather than a research tool. So
just to comment that Stephen himself will be very excited to know that there's people who want this. It's just
I think there's something kind of interesting about this sort of like, I can take a rule, and if I could scale it up enough, I could actually solve really interesting problems. And I don't know if that's like, I don't know if we're emulating some other thing, or if like the other thing that we see or are these analytical solutions are just approximations of this thing that we're simulating. Like, this stuff is very deep to me in a way that I can't really put into words very well. But
it's super interesting, and we should definitely, because as you mentioned, the backlit is even in prototype phase and kind of like still sort of developing. and it has a focus on really the symbolic side of things and diagrammatic kind of thinking. But it should definitely be have this in mind. So the fact that this connects not just as an application that is down the line, but actually mathematically and conceptually is so powerful that it's just the perfect match. I mean, it's a match made in heaven here.
Yeah, I have two other demos also that are similar to this that are kind of in work where instead of solving like a diffusion problem, I was going to try and do like a chemistry problem or like something, a lot of these like transformations kind of look like chemistry. I think this came up in Nicholas Baer's work talking about chemical reaction networks and talking about sort of the same sorts of behavior. And then I have another one where I'm just doing like my old linear time invariant circuit problem and just solving like a flow through a resistor. I have this sort of like working theory that you can kind of emulate a resistor by having low resistance, which is just conductance, right? It's just having more binary edges between two vertices, right? Like you'll match more frequently, using this flow rule. If I had, like, for instance, if I took this simple graph, let's do it live. What am I talking about? Okay. So what if I took, this is always dangerous when you off-road like this. I'm going to make 2 copies or 3 copies of 2, 3, right? Okay. So what are we actually doing here? Let's draw it. So what we have here is all the unary edges are bunched up on one side still, but now I've made a superhighway between 2 and 3, right? So what does this look like to me? Well, the engineer in me is like, oh, it's a circuit with higher conductance or lower resistance through this, between these 2 nodes.
Yep.
Okay. Let's see how well the re-execution works here. I probably messed something up is the short answer. What my hypothesis is that we'll match much more frequently to oscillating back and forth between paths here. Like it's just in proportion to the presence of these edges, right? So there's like a way to, I think, one thing that the physics project kind of highlighted to me is that there's this idea of varying dimension, and that has to do with the connectivity of things. But I almost wonder if you have multiplicities like this, if it isn't almost a separate thing as dimension, or maybe tell me if I'm crazy here, like repetition of these edges almost looks like a resistance or a path, a cost of traveling through space, a change in like a cost of some difference in a field. I don't know, like
that is intuition that I mean Nick was pointing at it with this idea of multiplicity counts as functions, and that's kind of it's almost like you can have a space of some dimension, but then if I have 80 edges all between 2 nodes, it's almost like there's some sort of path cost there, right? Or a weight or something like that. Okay. So I think you have
to change the percent now.
Yeah.
Oh no. Yeah, you're right. It's, what is it? 48 now. 48.
You should have called it somehow.
Yeah.
I know. Like I said, when you do it live, that's the risk. Okay, something has a 0 in the out degree, so there is a terminating state apparently. Or maybe I just haven't run it long enough.
Yeah.
Let's break this thing. Okay, I'm gonna hold on. I want to save this before I crash my machine.
I wouldn't try 8.
Oh, why not? You have to have a sense of adventure, man.
For 5.
I mean, people come for the suspense of will this run and break Sam's laptop or not. Do it for the drama. Okay, we may be here all day though.
Yeah, that's
okay. Well, I'm sorry I ruined your live stream now by crashing my computer. But we can kind of put a button on diffusion equation, and hopefully this hasn't been a complete waste of your time.
No,
I definitely learned a lot.
We can leave it running. We can leave it running and talk about the wave equation. Very interested to do some live brainstorming about how we could get the wave equation.
Contrary to the diffusion equation, I got nothing for this wave equation, but I'm very keen to figure out how you could do this. Okay, so for those of you that have an engineering background, a wave equation to me is just, the wave equation to me, I always, like I took a class on PDEs and I was kind of, oh, this is interesting, but a lot of the time when I model systems, it's almost like a wave equation at each node where there's some second order system that's present and there's a network between them. And when you have these like meshes, each of the individual elements of the mesh is a second order system, right? Where you have these sinusoidal solutions that are the fundamental solutions to the wave equation that are present at each nodal location. So I usually come at it not from the continuum like wave equation where space is continuous, but as networks of things that individually can oscillate. And if you look at the Wikipedia like derivation for this, they actually have a pretty cool derivation to build intuition that is just talking about springs and masses that are distributed in some network. Okay. Yeah. So if you guys squint, that looks like a hypergraph to me. I don't know about you guys, but that starts to look like some kind of graph where you have these masses at each of the nodal vertex locations, and then you have these springs between them. Okay, our edges aren't springs. We're not proposing that they are. But you could definitely have a continuum that is approximated with a bunch of discrete nodes that are all, meshed together with like a finite difference code for the wave equation kind of does this. It says the nodal locations are where I'm tracking the state of the field, and then my relations between them are just these sort of differential relations between nodal locations. Okay. Yeah.
May I tell you?
No, go for it.
May I tell you a brief anecdote?
Yeah.
It's very. I like this a lot because at some point when I was right before going to uni, I was very keen on understanding where the differential equations of physics came from, like wave equation, heat equation, and so on. And because I think I learned about maybe the wave equation or some of them with this, this kind of argument that you sort of discretize and you see how the elements relate, and then I made it my hobby during a few months, just like going around and thinking, okay, what would be the differential equations that models that? Because and what really got piqued my interest was I was once at an apartment, my grandma's apartment, and there were some works going on in the facade, and there was a hanging rope from the 5th floor or something all the way to the ground. So I remember looking down and with the rope and just like wiggling it and seeing like a pulse sort of like traveling down, and I thought, okay, could I just count like meter the time that the pulse gets to the ground and actually deduce the height of the building that I was in?
Yeah.
I thought, I can directly measure with some clock very, very accurately for the scale. And so I did, and I assumed that the wave equation held for that piece of string. And I was in a 5th floor, so maybe like 25 meters or something above the ground. And I got a result of like 500 meters. And I was like, yeah, this is clearly off, like by 1 order of magnitude at least. This is very wrong. So I didn't know what was wrong, what was like going wrong. And then I thought, so, I was just applying wave equation to a hanging rope, right? And I was like, wait, why doesn't this work? And then, I was applying wave equation. So this is the thing. I was applying wave equation where the tension was height dependent, right? So you take the formula for the speed propagation of the wave equation, you know that the tension is there. Normally it's constant or locally constant. In this case, I just said, okay, I'm going to change the tension by whatever the rope mass determines at its height, right? So it gave me a neat little differential, like ordinary differential equation to solve, to integrate, and I could do it by hand. I was like, oh, so fun. And I did the calculation, and I got 500 meters out of the experimental data. I was like, oh, there's something very wrong with this. And I was pretty sure the mathematics was all fine because it was quite easy. And I was like, what's going on here? And so I had to go all the way to like the definition of the wave equation in terms of like the fundamental mechanics. I rederived it for the case of a hanging rope. So when you have non-constant tension, and I actually found a different equation. It was a non-linear equation that happened to have
like dispersion, like a change in wave speed with it or something like that. I can't remember what that's called. It's like a third derivative or something with.
I think it's more it's second order still, but it's non-linear. Okay. It has some non-linearities, and I actually found that it was I got the equation. I was like, okay, I don't know how the hell to solve this, so it's not going to help. But at least I found in the literature that was indeed the equation that a hanging rope or hanging material normally satisfies.
Yeah,
so
tension.
Anyway, yeah. So anyway, so just as an anecdote, that at one point in my life, I was really making my hobby to just like try and understand where these equations came from. So it will be very fun to do the same with rewriting now.
Yeah, I in high school I was not that smart, so I only learned this stuff once I went into the engineering world, and they're like, all you need is a second order system to model anything on the planet, and like everything is just mass spring damper basically. So you treat everything as like these networks of like mass spring dampers, and the networks get increasingly ridiculous, but that's like all you need to simulate very complicated physics in many cases. But yeah, so there is like some, like you were talking about, sort of there's a if you look at a unit of rope, there's a force on that rope. It has a finite amount of mass. There's a differential force on either side of that element of rope that's proportional to some like spring constant of how much does displacement relates to the change in force. So I think hopefully that part's pretty intuitive for folks. I think everyone has a lot of experience with waves. Maybe not as much experience with sort of the wave equation, where you have a second order derivative in space. And now one thing that we kind of glossed over is the heat equation is a first order derivative in time. This one is a second order derivative in time. That's really the only, I don't know. I'm glossing over a lot of mathematics here. Someone on the chat is probably like, this guy's an idiot. Like, I just see that this order of the derivative in time is different. Otherwise, this looks kind of like the heat equation in many cases.
Yes.
There's a question in chat about whether you played around with the relativistic heat equation, heat conduction.
So no, I if you guys ask me questions on quantum mechanics or GR, I'm going to be like, yeah, that sounds cool. I wish I understood any of that. I've never actually had any practical experience with that type of stuff. I'm looking to you to explain that stuff to me. So,
so let's try and think about it, because I think the key difference between the heat equation and the wave equation is that one is first order time, the second is second order time.
Exactly.
So
I have like two thoughts on that. And you can tell me how dumb these thoughts are. I kind of have this working hypothesis. You remember how I said I really want to be able to do self loops of different arity? I two things kind of pop out to me with this is when you have these characteristic solutions that are sines and cosines, or like e to the I theta or whatever is really the fundamental Euler equation or whatever. Like, I kind of wonder if there's a complex number that we need to have like a real part of our field and a complex part of our field. So like, part of me is like, unary edges are the real part, binary self loops are the complex part. And can I define a rule where I'm cycling between those two things in the same thing, and that's my phase of oscillation, so to speak? So that's one thing. And then the only other thing I had to maybe contribute was, like those are kind of analogous to like, if you go back to this Hooke's law derivation, you're integrating two states, right? Or you're integrating acceleration to get an instantaneous velocity of that node on the spring, or sorry, that node in the rope, I guess, to use our previous anecdote. And then, but you also have to integrate that velocity to get the change in displacement. So there's almost like two integrals here. And that's obviously, the smart people have already figured out that second order is what drives that. It took me a while to figure that out. But yeah, I almost wonder if there's two quantities or scalar fields that you have to like independently flow or transform or accumulate or something like that.
I don't think we need to, like, I think the full analogy is, instead of temperature on a beam or something like before, right, on a rod, you could think of this vertical displacement on a rope, on a vibrating string, or just pressure on a tube or something, right? So you could equally think of a scalar quantity on a one-dimensional space as a sort of a toy model of how to think of the wave equation. What I think is interesting here is that and I was talking to Stephen about this for a couple of times actually in our meetings. The notion that it seems that rule application is in some sense it's first order dynamics, right? Like it's direct change. So it's in some sense it's first order dynamics. So I was kind of toying with the idea of, that is analogous to velocity somehow, right? It's like discrete rewriting velocity is like how you change from state to state. It's like the delta in state somehow. It's like this.
It's like a rate equation, right? Yeah. It's like a rate equation, maybe is the way to describe it. Like there's a first order time derivative aspect to it.
Exactly. And so the second order of it, I mean, as we know, acceleration is the velocity of velocity, right?
Yes.
So, I was starting with this idea of like, what about rewriting of rewriting rules as the concept for acceleration? And like,
oh, whoa, okay.
I mean, it sounds a little bit mind-bending, but I can't imagine there being a similar, like the analogy. I mean, I don't know. I don't have a good proposal of how this will work in practice.
Well, let me throw a proposal at you, and you guys can tear it to shreds. Right. Okay, you ready? Sometimes this is more fun, is to give the wrong answer and watch how people freak out. Sure. And this, I'm gonna be that guy who's like, here's my answer, and watch everyone say it's wrong. Okay, what if in that vein you had rules where the output of one rule is the input to the next, and like when I say the output is the input, what if you had rules where the output is transformed into some quantity that only be matched on a different rule? Okay, maybe that doesn't make any sense. Here's an example. I start with a single unary edge, and the output of that unary edge is a binary self loop. And I've actually played with this a little bit too. Like my first iteration of this was I take two unary edges, and there's a transformation to turn those into a binary self edge. But then there's a second step where that binary self edge has to decay. This isn't conservative, so like I've already messed up my own like demo here. Let's actually run it, or I guess let's just do this. Yeah, this is my original, but like there's all sorts of categories of this. But imagine if then there's another rule that matches only a binary self edge and a regular binary edge, and then it vects and decays back into a unary edge. Okay, now here's how I got to this point, which is like I need to accumulate some velocity, but velocity doesn't equal displacement. That takes another amount of time for that velocity to translate into displacement. So like I almost have a rule whose output is a change in velocity, and then that velocity results in like flow or displacement of the system. Now, this isn't right. I know it's not right, but sort of the idea was like the output of one rule is the input to another, and you wouldn't have rules maybe competing for those outputs. They would just form chains, but they would form like a cyclic chain where the output of this rule, right, after it decays back into a unary edge, is the input of this. And this kind of toy system you can simulate. So for the new folks, this is just like an evolution events graph. This is just showing all the matches, right? So I have a single unary edge that turns into a binary edge. That binary edge and self edge and simple edge cause that to advect down to node 2. So now I've started with almost the reverse of my initial condition. So this is like 180 degrees out of phase, even though it's like out of phase in space, but not out of phase in like local for a given vertex. I guess it is kind of, because now I have 0 unary edges at 1 and 1 unary edge at 2. But then I can keep applying this same rule set, just literally sequentially, and it's a cycle. I will always get back to my initial condition, okay, for this graph. So part of me is like, oh man, this kind of reminds me of like, okay, that's 0 degrees. This is 180 degrees, and then I'm back to 0 degrees. Now, part of this is a result of the structure of the simple edges that I chose, but it was like, is there some sort of like cyclic rule set that could emulate wave equation behavior? And I'm not sure exactly what that looks like, but my first crack at it was go to higher arity unary or higher arity self edges as your like complex number part. When the real part goes to 0 locally, you still have the complex part or something. I don't know.
I mean, that sounds very intriguing. I can't really say this is wrong in any way.
What did you guys say the other day? It's not even wrong.
No, that's the worst. That's the worst possible.
That's the burn.
That's the worst possible critique to an argument. I mean,
yeah.
Which is absolutely not the case here. It's absolutely not the case here. No, but, and I say it because it really is uncharted territory, in my opinion. Like, how I'm just constantly running through different. So composition. So you're alluding to something here. You're alluding to composition, right? Essentially, which is sort of sequential application of rules, which it's actually interesting. I was kind of dismissing composition as part of higher order until you said something like, velocity takes some time for displacement to happen, which is kind of what you want to infer in acceleration, meaning that you can affect the velocity state so that the actual displacement will be different. So
exactly
in that sense, there's definitely something going on there that sounds right.
And the thing that got me there also was just every kind of undergraduate like myself in engineering knows that nobody actually like when you're integrating these things in MATLAB or in Python or whatever, nobody actually like does a second order system solution unless they're really super big brain people. All we do is a linear system of first order equations, and it's rank 2, right, of that linear system, right? So it's like okay, so all I need is 2 independent variables as my basis variables, and I can emulate this second order behavior, right, and just relate them through that state transition matrix or whatever.
I mean, and that's a non-trivial. That's not just a trick. Like that I would say is deep in how we do mechanics and how we do differential equations. The fact that you can effectively with that geometrically for people with mathematics background, that effectively means instead of working on space, you work on a tangent bundle, and then your second order dynamical system is a first order dynamical system on the tangent bundle of your first system. Right. So so it's not just a kind of a trick or like it's actually a very well established and very sound mathematical statement.
I don't want to seem too clever because I felt like that was just a hack that I learned in undergrad that I was like, this is great. I could do like all sorts of stuff without having to know what the fundamental solution is.
It is very sound and actually thanks for mentioning it because but in some sense, like in a way, it's kind of compounding on my point that this idea of rewriting because essentially what that makes is the space of changes, the space of velocities, the space of rates of change into your dynamical space, into your sort of state space, right? Yes. And then you take and you can do this, indefinitely, sort of higher towers of higher order systems. There's no mystery there. So I'm thinking.
So this is why I was kind of pressing for you not to dismiss too early my higher arity self loops, because you're going to wreck my second order system game if you do.
No, absolutely. Yeah, like so, we should be able to do self loops. Like this should not be a no go,
a breaking change or whatever.
Not.
Yeah,
it should not. It's just that how exactly we do it is the question, right? We're at no point we are saying we don't want self loops. Like that's stupid.
Right. No, I got you.
But the point is like we might want to like recover them with labeled structures so the arity is actually regular and things like that. But that's a different story. It's more about implementation.
It's such an edge case too. I know I don't want to like drive the development of the hypergraph and multi-way packlets in a direction just to solve this use case that like realistically is kind of like no one's going to be doing this except for psychopaths like me. But like I think that this is super interesting to sort of freeze the topology of the graph and just use these unary edges to encode fields on the graph. That alone to me is kind of interesting. And then obviously the whole space of what you can do with hypergraph rewriting is much bigger than this, right? Yeah. You can do mutating the edges dynamically and stuff, which is even cooler.
And so I would try to follow up from what you just said as a summary of what we did in the sort of example of heat equation or the diffusion example, which is that in that case, the intuition that unary edges essentially encoded a scalar field.
Yes,
it's very natural, right? Everyone understands this. Like, this is what we intuitively mentioned and a few streams back, and that's what you heard us say, and so on. So I wonder, a natural question here for the wave equation, even thinking before second order dynamics and what that means in terms of rewriting, would be, what is the dynamical object that we're trying to encode in our hypergraph? Like, what is the analog of the unary edges that represent the scalar? Because typically in wave equations, it can be a scalar, like pressure or not.
Oh, absolutely, yeah, right? yeah.
So it could be that just the unary edge is enough, as you said.
Yeah.
But then I wonder.
But remember, pressure is changing. Like, I don't know, I'm probably going to embarrass myself here, but like pressure's changing because there's a non-zero velocity component too, right? Yeah. Like, you're trading total and static pressure.
Yeah.
Here's my engineering background coming out again. Like, you're trading stagnation pressure and dynamic pressure for velocity, right? And so you're almost like transmuting. I'm gonna go full. What is it? Isaac Newton back in his like alchemy days. You're like transmuting pressure into velocity. Yeah. So the pressure hasn't changed. It's still kind of conserved in a weird way.
Usually the wave equation really shows up when you do a quadratic approximation of any kind of force interaction, this shows up, right? And that's when you can characterize, morally speaking, I guess, you can characterize the state of a system around some equilibrium as a displacement from that, right?
Yeah. Yes.
So, and that's quite different from something like heat or like a gas that diffuses, because a gas that diffuses is not really a displacement from an equilibrium. It's more like an absolute quantity that is being spread out, right? So I wonder what is a good graphic analog of this idea of local displacement from an equilibrium. It's like,
and that actually raises a really interesting point that I kind of forgot to make about this diffusion equation, which is I show you the graphs where it works. I don't show you the graphs where it doesn't work, right? That's like how all science works, is I only publish the stuff that's interesting, not the failures. But there were a lot of failures to get to this point. And I'll tell you one failure that's particularly, I think, relevant for this wave equation, which is if I don't sprinkle enough unary edges such that there's a high signal to noise ratio in the equilibrium from zero. Like, remember, we can only encode positive integers effectively on these vertexes, on these nodes. If I put not enough unary edges such that the equilibrium is significantly above zero, I get stuff that doesn't make any sense. Right, because it essentially just looks too sparse to be like a continuum, like our analytical solutions that we expect, right? Yeah. So there's some level of initial sprinkling of these unary edges to get the analytical results we expect, right? Analytical results we expect to look like the diffusion equation. This thing has to be sufficiently packed densely, so that you're just oscillating about something which is non-zero.
Yeah.
Okay.
Yeah.
So I suspect that the wave equation will be similar in the following regard. We will not be oscillating about a zero. We will be very offset from zero in terms of we'll have lots of unary edges throughout the domain. And like you said, we'll be oscillating about that equilibrium. But to get a good result, we will likely have to sprinkle, densely pack,
Sure. Yeah.
There's like a critical threshold, like a Knudsen number or whatever in fluid mechanics where you talk about continuum versus non-continuum.
Yeah.
I see that in these systems as well, where like we're never going to get a negative number, so it's definitely not that, but we're definitely going to oscillate about some non-zero positive number, I think.
Well, actually, I take your point about minimum density, minimum population. I think that's clear. We're going to get artifacts otherwise, but I actually think something that fundamentally it's kind of follows from I said in my previous comment is like the heat equation doesn't have a sense of there is less than here than more. You can compute local differences, obviously, but the stuff it's an equation about stuff in space, right? But the wave equation is not about stuff in space. It's about difference of stuff in space in a way, right?
Yeah.
Probably that's also indirectly why it's second order, because and in a sense we do want to be oscillating around the zero, in the sense that it's not because it has to be a zero in some algebraic sense, but because we do want to get the notion that there's a sense in which you can be globally below and globally above, which is not possible for the heat case, right? Like there's no sense if you have your entire sheet and it's vibrating, like you can just lift it up as a whole, right, with a magnet or something, and just release it, and it will oscillate, right? But the analog with the heat equation or the diffusion is that if it's already in equilibrium and you throw more stuff like uniformly, you just raise the equilibrium and
you just raise it,
right. So I think that's going to be a difference in how to encode it. I mean, I'm still completely undecided about your suggestion of having like this sort of. I kind of like this idea of two states. Like it's a neat way to precisely encode sort of positive, negative, sort of above, below kind of encoding. Yeah. It's actually very interesting.
The part I didn't know is like, how do I encode a negative velocity? But maybe, like you said, if you're really only tracking a single scalar potential, that negative velocity is encoded as a difference.
Yeah, I think negative velocity could just mean that you're going from a positive to negative. Right? If something like if you call one of your patterns positive and the other negative, doesn't matter which way, but then positive to positive is positive, negative to negative is positive, and then positive to negative is negative, negative to positive is negative, right? Like this kind of, like it doesn't, like, I think if you have something like states that are locally representing, I think that's right. Sorry, I'm thinking on the fly.
No, it's okay. You're like me though, where I think you verbally process some of these things, and so sometimes it's just a matter of getting it all out, and then it'll make sense later.
Yeah. No, but I was just thinking out loud as an understanding as you were showing it, and I think your idea of having effectively, instead of one kind of unary edge, two kinds of unary edges, it makes sense. So
or like colored ones or whatever, just ways to distinguish between them and exchange, or I'll use this alchemy word, transmute or whatever between them, right? Transform them through rewriting rules between one and the other.
One way, I mean, okay, I'm thinking of a way that it might be very directly, trivially true, but might not be so interesting. So imagine that you infuse some inner algebra to the. So okay, one way to understand it. Let me put this much more clear. So I was just thinking out loud. So if you have the case of the distribution of heat, right, with unary edges that represent some stuff, some mass, that is effectively like saying you are just considering integers, right? Natural numbers. It's just a natural number count, and that's it, right? So positives in that sense. But imagine that you now could allow for positive and negative edges, which effectively means that you are not just calling them, red and green or something, but you're really giving them an internal algebraic structure. So you would have a rewrite rule that is diffuse, like the one before, but they will be like black and white or whatever nodes.
Yeah.
And then when there's another rewrite rule, then when you find black and white on the same location, you delete them.
They cancel each other out. Yeah.
You delete them.
I was looking at rules that did that too, where like when you collided two nodes of a certain arity or of differing arities, they would like decay, or like they would bounce off each other or something. I was trying to think along those lines though, what you're talking about.
I'm now curious about what happens when
the one thing I'll say to your point though about positive and negative though is what's interesting about diffusion problems is typically the scalar quantities, there's no such thing as a negative value. And I'll give you some examples. There's no negative temperatures. There are on Fahrenheit or whatever, but whatever. Yeah. There's no negative temperatures. There's no negative concentrations. There's no negative, I don't know. What are some other diffusion
densities.
Things? What's heat equation in GR? What is that?
There are no negative densities, right?
There's no negative densities. Yeah. So like these diffusion processes are typically things that don't need to take negative values. Yeah. So maybe the wave equation is
different.
I would argue that the wave equation is about, you're measuring displacement about a mean, but that mean is non-zero in almost every case. There's no such thing as a wave equation in a media that is zero. There's no molecules, right?
Yeah.
Zero molecules or negative molecules aren't a thing.
Yeah.
So I don't know. Part of me sees some connections of these like hypergraph systems that can only take positive energy values to like real physical systems where there's no such thing as a negative molecule. There's no such thing as a negative pressure. There's no such thing as a negative. Well, there is negative velocities. It's just direction, I guess. Is
what
it is.
But still, there's no sense of negative speed. Right?
Yeah, I can't have a negative kinetic energy. I can't have a negative momentum. I can't have, or wait, maybe I'm embarrassing myself here. And there are all these things, and you guys are just not calling me out on it.
You're preaching to the choir here. Like
okay.
I mean, you totally get what you're saying.
So yeah, I'm full of opinions. If you want to listen, so just feel free to shut me down anytime.
Yeah. And one thing is, Nick, just for reference, I mean, the random comment here, to pick your brain for a second. What do you think about if I say, just one kind of unary edge bosons, like two kinds that have that sort of like canceling rule, fermions?
No, it's not obvious how would you extract the actual statistics. But what exactly fermion, for the fermion, what exactly corresponds to the Pauli exclusion principle then?
Yeah, maybe that's the problem. It's not really fermions. It's like bosons and anti-bosons, right? But it does seem to have like the behavior of a displacement, right? In a wave situation, it's precisely that you have something that travels like a packet, and it on its own, on a background of stability, it behaves like a bit of temperature, a bit of density, mass, whatever.
Yeah.
But there's no analog. Typically you don't have like a bunch of negative mass that just subtracts mass. But in the case of displacement, you have precisely that. If your displacement is with the same amount of energy but in the opposite direction, there is a sense in which you can cancel. So there's something very intuitively direct in the phenomenon of canceling displacements, in having two kinds of unary edges that you add an extra rewrite rule, which is basically the cancellation rule, right? Like if you have two unary edges of the same color, nothing happens. There's no rule for that. But when there's one for one and one for the other, then you have a cancellation rule, right? Which is exactly the arithmetic that you are looking for, right? It's the arithmetic of, if I have 5 up and 3 down, I actually have 2 up, right? It's that sort of. I mean, the thing with fermions was just like to throw some sort of particle physics stuff in the conversation. It wasn't the.
No, I think that there's like, obviously, it's almost, there's just analogs in all these different domains where, like, even if the output of this was just like something that kind of looked like the wave equation, that we could mine for something interesting in terms of like what kind of rule produces the wave equation. I think that's an interesting finding, because it's like,
for sure,
it applies to so many different domains. I don't know. And what you guys are talking about with fermions, I just think about analogies to chemistry of like, there's only certain transformations that are allowable. And if you put 2 of these molecules together, there's a free energy minimization. They'll just react and transform into this third thing. I was playing with rules with like conservation of momentum. Like how do you like have a unary edge that indicates momentum, and it just moves, it translates. But then when it runs into something, it can like pass that momentum to something else, like a billiard ball, or like I was playing with some really dumb stuff. I'll give you guys one more kind of like another way to look at this. Like maybe we don't look at it from this higher arity self-edge approach with like, I think of it as like a complex number. Okay, just table that for now. When I first started looking at these things, I started looking at these finite difference rules, which I don't know how much you guys play with finite differences in your work, but like in engineering, this is like a fundamental numerical skill to understand, is like this concept of like approximating a continuous derivative with a discrete difference between two locations on a mesh, on a grid, on a spatial domain, whatever. And of course, if that mesh is fine enough, gosh, it sure looks like a continuous derivative, and it sure looks like the analytical solution. So there's like some resolution that's required. But so if you look at how finite difference codes solve the heat equation, you'll find that the rule we defined actually kind of looks like, I'm going to pull up this PDF. Hopefully it loads. Yes. Okay, so this is credit to Gerald Rechtenwald. If you actually look at the finite difference approximation, the way to read this is we approximate a continuous spatial derivative as a scalar field, value at the I+1 grid point minus the I grid point. Okay, now burn this into your brain for 1 second. Now look at this. Yeah. We see a difference between grid point I, I'm just going to call this I, and this I+1.
Yeah.
And that's the spatial derivative. Okay, so that's kind of interesting. So think of differences in unary edges are this discretization. And then let's talk about the time derivative. There's many ways you can do a time derivative. Oh man, why can't I zoom out? Whoa, I thought I found this exact expression I was looking for. Okay, so first order. This is all spatial derivative stuff. This is what I want. So you're saying that the rate of when you break this down, you're solving this equation. They've replaced the spatial derivative here with a finite difference. But what if you replace this with this phi at time m+1 minus phi at time m, right? Mm-hmm. So typically there's a negative sign in here, but basically we've encoded the forward temporal finite difference and the forward spatial finite difference as a rewriting rule. That's my kind of maybe claim. I'm probably wrong, but I think that's what's happening here. So then that kind of led me to the belief that, let's look at what they do for the wave equation. So I think I have a link up here for the wave equation for kind of a similar resource. Again, so this one is using what's called the center difference, which, some of the folks online are going to know immediately what that means. Some aren't. But like when I talk about forward differences, think of it as a one-sided difference, right? So you can discretize the derivative by taking a perturbation in one direction, measuring that difference, and then dividing by the perturbation size, and that's your local derivative, right? A central difference is where you take the difference in two directions from the point you're trying to evaluate, and then you kind of average the two. So then you get this thing that's really a function of three nodes. So in this case, they're doing center difference in time, center difference in space for the wave equation. And then they talk about some of the stability properties of this. But what you end up getting is, if you squint a little bit, let's go down here. This is the stable scheme that they're talking about. You end up getting, okay, let's look at how to read this, because this is like, to people who deal with meshes, this is like obvious, but it may not be obvious. The sub-index is the spatial index.
Yeah.
Okay. And the exponent is the temporal index. Mm-hmm. So what we're saying is that the future time step value of the field at node I at J is a function on the right-hand side of the neighboring one at time step, the current time step, in one direction, the other direction, and then also the value at J from the previous time step to the current time step.
Yeah.
So there's like next, current, and previous. N-1 is the previous. So to kind of what you were talking about earlier about maybe there's not a need to define this sort of complex number. Maybe it's just a time history of a single unary edge field. I don't know how to encode that or have that sort of differencing possible. Yeah. Like what is a rule that could look back to? I don't know. I think that's what I was going for when I was going for a rule that feeds a rule.
Yeah.
But like, if you think about the simplest possible solutions to the wave equation and how you can update the field versus time, it's almost like you need a rule that a stencil is typically a finite difference. We talk about stencils, right? Like the stencil of grid points in time and space. You need a stencil that can look back to in time. I don't know what that looks like from a rewriting perspective.
Yeah. So the one comment I have here is that, I mean, if you want to refer to that formula for orientation, is that the J+1, J-1 pattern, where the fact that you're checking like around your grid position, that should all be encompassed by a single, but like the single input state of your rule, right?
Yeah.
And the fact that you refer to a previous state,
it's almost like it's an end. If you think of, so the one caveat to this, which you correctly point out, is that the fact that we need two neighbors at the current time step is principally a function of their choice of spatial differencing scheme, which is the central difference. But as we saw with the diffusion equation, this kind of just looks like two applications of a forward difference on either side, right? Like in a weird way. And I suspect you could do a second order derivative. Well, could you? I don't know. I'm probably embarrassing myself here.
No,
could you do a forward difference second order in space? Like, I feel like there's something dumb here where the equation I was looking at for the heat equation comes from Fourier's law and not from the heat equation or diffusion. I'm mixing something up here, but I think the choice of this finite differencing could define, like you could do a forward finite difference. Okay, let me back up one. So this is a central difference, second order, second derivative in time. You can also do a forward difference second order in time, or a backward difference second order in time. Yep. But the relationships are still the same, where you end up needing three sets of grid points. It's like they're all related to each other. The n+1 will still be related to the one -1 and -2 previous, no matter how you do this. There's always like a chain of the third one is a function of two others. I don't know if that makes any sense.
Yeah. Totally.
So
no, I was just thinking that this might be naive to claim at this point, but it feels that spatial derivatives should be largely covered by essentially the topology of the input hypergraph. So in the rule.
Yeah, agreed. 100%. Yeah.
But then
that's your mesh in my mind, right?
Yes,
like that's your spatial domain.
Yes. And so, I mean, the analogy seems to be in this sort of infrageometric mindset. It seems to be that if you are at 1 degree separation in a hypergraph, that seems to correspond to a first order derivative in a way. Spatial.
Yeah, agreed. Yeah.
And then if you are at higher degree separations, like longer path separation, then that would probably correspond to some form of higher order spatial partial derivatives.
Actually, that's a great point to point out. Is like in finite difference, you can have higher order derivatives of a certain, higher order derivatives of a fixed order derivative, right? I could have a first derivative, but I could have a third order one that has three neighbors in space, not just the local first neighbor, right? I think that's what. Did I say that wrong? Probably, but
no, I think that's right. Because I mean, Can I see?
Like this is kind of illustrating that like a central difference method that's second order relies on 3 grid points on the spatial stencil, but you can also have a second order forward. This is a second derivative. But I have a book. I'll find my book. Like I have a table of these that I referred to. Unfortunately, I'm not going to hold the book up on my camera here, but like I have a table of these where you have the first order derivative, but I could have a 5th order approximation of the first derivative where I need 5 neighboring meshes, and there's a stencil of like, it's like a butcher tableau for Runge-Kutta. There's a fixed integer multiplier for each value at each scalar. And so you could derive like a higher order first derivative by looking at many neighbors, but having certain multiples of them. So
definitely. Yeah. No, I think that's clear. No, the real question is how to think about acceleration rewrite. I mean, Nick, do you have any ideas? Have you ever thought about this kind of direction? Is this too psychedelic for your liking? How does this?
So the second order. Yeah. Well, I don't. Similarly, I don't think like the time particularly makes sense. Second order of time derivative does make sense too much, right? Because you can always reduce it to the first order, right? It's just like like you said, if you derive the velocity, then you derive the
like a system of first-order equations from a second-order rule.
Yeah, but the way you do it, like you can do it formally. Like it works for analytical purposes, algebraic purposes, this kind of like integration purposes. That is like the language of calculus. But when you think about what you're doing there, right? Like conceptually, you're only just doing a fancier sounding version of I'm taking my velocities to be my states, and then I'm just doing velocities on my states, which are now velocities. So it's velocity of velocity. So I feel like in a sense,
on the graph you kind of have a natural notion of velocity. You have edges, right? So you can think of a first order velocity rule rewriting is something that modifies the edge multiplicity or something having to do with edges. And another rule, the second order rule, would be something that has to do with edges more. Right? So
but that's thinking of a graph that is like where nodes are like states and edges are like velocities or something.
Yeah, perhaps.
Yeah. But
yeah,
exactly.
You have a tangent plane.
Okay, so
right?
I'm going to take that and I'm gonna use it for my own argument, which is okay. Now instead of a generic graph like you were probably thinking, imagine that that's your state graph of a particular rewrite system, right? Like that graph comes from a rewrite system. That's exactly what I mean, right? That if you think of states, those are the states of your rewriting, and the edges, directed edges between them, those are the velocities, because those are the events, right? Like the rewrite events, those are velocities, right? So if you think of doing rewriting on that graph, right? That seems like acceleration in some sense, right?
So you're saying like rewriting on the states graph. That is a concept that I'm having trouble visualizing, but I suspect if I thought about it for a while, I might get it.
I was actually thinking more specifically about not rewriting on the states graph in the sense that that's just a directed graph, right? Like you just have some directed graph. But I was thinking that because a velocity, how to say,
can I I'm literally terrified right now. I don't know if anyone in the chat was pointing out that my battery is low and I'm not plugged in. So I'm terrified. I'm just gonna be like, oh, that's a great, and then drop. So I'm gonna actually go grab my charger for 1 minute and also time check for you guys. I kind of need to bail here shortly.
Oh yeah.
And we're at the full time, but like obviously if I had my choice, I'd just sit here all day and just hang out on this live stream. So
It's very good to wrap up. I mean, I think it's a good time to wrap up, and I think there's a lot to go on here, and I think we can obviously invite everyone to continue on the Discord, but
please.
Sam, with you particularly, we'll be very happy to meet, not maybe outside of a live stream or continue with this. This is super interesting. It is super aligned with everything that we've been thinking about. I mean, it really is a blessing for me. Like I have to tell you very, very sort of personally. I mean, maybe I speak for Nick, I speak for James. Like in running the institute, there's been many bumps, and as you can imagine, like the organization side, we're sort of trying to get things together and so on, and things are looking really much more stable now. But like this is kind of the dream scenario where we get super cool people like coming and using our ideas and engaging and obviously infusing their own, because I think there was a lot of you on this, and I really appreciate.
My journey was integral to me, even like identifying that this could be possible. I think a little bit. So if it's any encouragement to folks who are watching the live stream, like go download the Packlet and try this out. Like worst case scenario, nothing happens. That's not really that big a downside, but best case scenario, you might find something really interesting. So
yeah, absolutely. Thank you so much, Sam. Let's be in touch. And thanks everybody. Thanks Nick for your time, and thanks James.
I'm gonna go charge my laptop. Bye guys.
Bye Sam. Thank you. Goodbye.